Good day, everyone. Good day, class. Welcome to our Electronic Devices 1 class. My name is Dominic, and I believe you're already done with your basic electronics. In this course for our Electronic Devices 1, I wanted you to have a very good background of your basic electronics. And since you guys passed, so I believe that you're already done with your Electronic Devices 1. So, before we go to the main discussion of this electronic devices one, I'll just give you a quick tour of some of your basic electronics lessons. But definitely, I will not go back anymore with Ohm's law and how they are being derived and everything. So, we're going to start with the definition of electronics, and we will just go slowly into how electrons move, because that's what really is very important, and on how it affects our current devices, just like our PN junctions or our diodes, our field effect transistors, and even our bipolar junction transistors. So let's start. So just a quick recap. So what is electronics? So it is the study of flow and control of electrons. So when you have a flow of electrons, there you can create electricity. And the study of their behavior and their effects when you talk about vacuums, gases, semiconductors, and with devices using electrons. Okay? So when there is flow of electricity, or when there's flow of electrons, that is where you can create electricity. Okay, so do you see electrons in your basic electronics one, in a certain copper wire? If not yet, then I will lead you into that. Okay, so also by definition, electronics belongs to the big umbrella of electrical engineering. Okay, so let's start with what is electricity. Okay, it is a phenomenon that occurs throughout nature and takes many different forms, just like our lightning. It carries high electricity, high current, and even high voltage. Okay, it is electricity that powers our electronic gadgets, our cell phones, our refrigerators, our air conditioners, even our calculator. There is current in there. Okay, our laptops. Okay, and electronics is just briefly defined as the flow of your electric charge. Okay, so later in our discussion, we're going to answer where do these charges actually come from. I hope you're familiar with positively charged particles and the negatively charged particles. How do we move them? If I said that electricity is the movement of your electrons, then how do they move? Where do they move? And how does an electric charge cause mechanical motion to make things light up? Okay? So we will start with going atomic. So basically, we have here atoms, the building blocks of life and matter. Okay, all they call this, all materials are made up of atoms. Okay, it exists in over 100 different forms as chemical elements, just like hydrogen, copper, oxygen, what are as boron, and other chemical elements. Okay, and we have here from our chemistry way back our high school, we have our building blocks of atoms defined to be the protons, the positively charged particles, okay, these orange one here, our neutrons, the neutrally charged particles, and our electrons, the negatively charged particles. Okay, you have here. So in our periodic table of element, 29p is on what number? I mean, on what element? Okay, it's very, very common. Okay, so you have here your in our chemistry, also in our high school, you have here, this is our composition of our atom. Okay, and this one here, if you can remember, you have here our valence electrons. Okay, so you have here 2p, 8p, and then so on and so forth. Okay, so 29 actually, can you have a wild guess? Okay, 29p is our chemical element copper. Okay, and then also we're going to show you why do we have copper as a very good semiconductor device, or a very good conductor. Okay, so let's also start with how do charges flow. Okay, how do we move an electron to another electron? As what I have said, in one material, it is composed of many atoms. Okay, and in the one atom, you have there electrons, protons, and neutrons. Okay, so charge is a property of matter, just like mass, volume, or density. It is measurable. Again, it is measurable. In our chemistry, our charges actually has its own mass. Okay, just as you can quantify how much mass something has, you can measure how much charge it has. Okay, so in our in our chemistry, you have there our number of protons and number of electrons in one singular atom. Okay, so you have here the key concept of our charge. We have here our protons and our electrons. And then how do we move these charges? Because as what I have said earlier, we need to move these charges, we need to move our electrons for us to create electricity. Okay, so we're going to start with the electrostatic force called, it's very common, Coulomb's law. Okay, it is a force that operates between charges, and since neutrons, it has a neutral charge, so we're going to just neglect them in our flow of electrons. We'll focus more on our negatively charged particles, our electrons, and our positively charged particle, protons. Okay, it states that charges of the same type repel each other, while charges of opposite types attracted to each other. Okay, do you remember in your physics classes in your high school, we have there our experiments of magnets. You have there the North Pole and the South Pole. Same with our Coulomb's law. Those magnets, if you have the same poles of our magnets, if you have North Pole and the North Pole, then those two magnets will never get attracted to each other. Hence, the force between them is very strong. That they will never, that you cannot really stick them together. Okay, and the concept also of repulsion states that charges of opposite types, they're going to attract to each other. Okay, so in this case, if you have the negatively charged particles and the positively charged particles, so when you combine them together, of course, they will going to attract each other, just like our north pole of our magnets and our south pole of our magnets. If you remember, if we're going to stick them together, if they're in opposite direction, I mean, if they're in opposite poles, then there is a very strong force that will going to attract each other. Okay, and the amount of force acting on two charges depends on how far they are from each other. Tama? So just like our magnets, okay, if we try to play that, you have there let's say same poles. You have the negative for the North Pole, and you have another North Pole. And then if you wanted to get these charges attracted, so when these magnets are very close to each other, there then is a very strong amount of force that they will never really stick to each other. Okay, and also on the other end, if you have opposite charges or opposite poles, if you're going to attract them together, it is very strong if they're very close to each other. Okay, so the amount of force depends on the distance. So the closer those charges are, the closest these proton and neutron are with each other, then there is a very strong force that that pushes or pulls them away. Okay, so how do these charges flow? Okay, electrons in atoms can act as our charge carrier. Okay, so here in our outer shell, okay, you have here your valence electron. Valence electrons, it means that the outer shell is not complete. Okay, if we try to count these electrons, these actually are 29 also. Okay, diba? In our atomic number, or in our atoms, we will going to have an equal number of protons and equal number with our electrons. So these here are electrons. Okay, it has 29 electrons. So following in our chemistry, have 2p, 8p, so on and so forth. In our 29, which is copper, it only has one valence electron. Okay? And later, I will going to show you how it is advantageous to copper for our movement of our electrons, diba? If you see our copper wires, if you see our wires when we use our electricity, it is basically composed of a copper wire. And there, then I'll going to show you how does that happen. Okay? So, copper wire, again, it is filled with countless number of atoms. And in our copper wire, you only have one valence electron. Okay, so you have here copper wire, copper atom, atom. And then you have here your one valence electron. Okay, the chain effect, if we let this one electron jump to another atom, jump to another atom, then we can create electric current. Because as definition again, electricity is the movement of your electrons. Okay? So let's start with insulators. Okay? What are those insulators? Okay? Basically, you have paper, wood, rubber. Okay? Diba, if you have tried to observe, our copper wire, it has this rubber outside so that when we hold them, because we ourselves are conductor, tama, as a human being. Okay? So whenever we hold them, then if there's no rubber, if we're just plain holding the copper, and then it is connected to our source, then obviously we'll get electrocuted. Okay? So we need to have these insulators. Okay? And those insulators are what? Paper, wood, rubber. Do you remember in our physics lessons, when there is somebody getting electrocuted, we should not hold the person because you will get attracted also. What do we use them? We will going to use stick. Okay? Or basically we're just going to pull their hair. Okay? And those are insulators. And our insulators here, in its valence electrons, in each copper atom, it has so many valence electrons. As you can see here, it has 8 valence electrons for our insulators. Okay? Insulators, by definition, they have tightly bound electrons in their outer shell. Okay? Okay? Very much there are so many electrons on its outer shell. Okay? And these electrons require a very large amount of energy to free them for conduction. Again, if we wanted these electrons to move from one atom to another for us to create electricity, then since there are so many electrons free for conduction, just like basic concept of force. Okay, if it's very heavy, then you need to really exert a very large amount of energy. Wherein if it's just so light, then you just need like a push, small amount of force needed or energy, then that material is just going to move. Same with our atoms. Okay, since there's so many electrons in its outer shell, then we really need to have a very large amount of energy. Later, I will going to show you if we apply potential difference, what happens to our outer shell bound electrons. Okay, so we applied here our potential difference or our voltage. Okay, did you see any movement of our outer shell electrons jumping from one atom to another atom? You cannot see any. Therefore, insulators does not conduct. Okay, it will not allow electricity to flow. Okay, from this illustration. Okay? Insulators are said to have higher resistivity or higher resistance. They resist the flow of current. Okay? In our Ohm's law, you have here V is equal to I over R. I is equal to V over R. If your R is very high, then your current is very small. Therefore, insulator is said to have high resistivity. It will not allow flow of electrons. Okay? Did you understand? I hope so. Then we move to our conductors, just like our copper, our silver, our aluminum. We also have definition of superconductors. We have gold. Okay? So just like here, our copper in our chemical symbol, you have here copper as number 29. Okay? And by our chemistry, how do we arrange these electrons? You have only one free valence electrons for our copper atom. Okay? So later we're going to show or we're going to see if these electrons here, if these one free valence electrons will really move from one place to another by applying potential difference or by applying voltage. Okay? Since this electron is just only one, So we just really need a very small amount of energy for this electron to be freed from its conduction, just like this. Okay, let's apply potential. Okay, did you see that? Okay, if you can see, our electrons, free valence electrons, okay, they are moving from one atom to another atom. Okay, and what did you observe? Try to observe the flow of your electrons. Okay, this is the negative charge, or this is the negative side of your potential. Try to see what happens. It is trying to repel the electrons because electrons is a negatively charged particle and tried to be attracted to our positively charged side of our potential. Okay? Therefore, we only need a small amount of energy to let this electron move from one atom to another atom, to free them from conduction. Okay? The force on each electron is enough to free it from its orbit, and it can jump from one atom to another atom. Therefore, copper, silver, aluminum, gold, and other types of conductors conducts. They allow the flow of your electrons given a potential difference. Okay? And conductors are said to have low resistivity or low resistance. Okay? Again, from our Ohm's law, I is inversely proportional to our resistance. You have I is equal to V over R. If your resistance is very, very small, then you will have current so high, you will have a current that can allow your material to pass. Okay, I hope you understood that. And next, we're going to go with semiconductors, the very main core of our electronic devices lesson. Okay, so you have there semi, so it means it's in between of the conductor and your insulator. Okay, then semiconductors have a resistivity or resistance between that of conductors and of insulators. Okay, so if we try to what they call this, recall our insulators, it has so many outer shell. It has so many electrons in its outer shell. In our conductor, it only has one. Okay, so maybe we can now have an idea how many free electrons are there in our semiconductors. Okay, their electrons are not free to move. Okay? But a little energy will free them from conduction. Of course, we need to have an energy for those electrons to move from from one atom to another atom. Okay? And our semiconductors, the two most common semiconductors are said to be silicon and germanium. Okay? And later, also in the discussion, I'll going to show you where does silicon come from. It's very, very common. It's very, very abundant in nature. And why, of all the chemical symbols, why silicon is actually being selected for our semiconductors. Okay, later we're going to know that. Okay, silicon. Okay, in our table of elements, okay, hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen. Okay, so on and so forth. Okay, so our silicon, based on our silicon atom, it only has 4 valence electrons. Okay, daghan or sorry, many, still many, but not that much and not that low. Okay, so again, the definition earlier, we need to have little energy to free these electrons from one atom to another atom. Okay, silicon has a valency of 4 in its outer shell. Okay, each silicon atom shares its 4 outer electrons with 4 neighboring atoms. Okay, remember, in one material, it is composed of millions of atoms. Okay, so for example, we have another silicon atom, another silicon atom, another silicon atom, and another silicon atom. Very good illustration. Okay, so you have here our silicon atom in one material. This is how it is being illustrated. Are we familiar with crystal lattice? Okay. Later, I'll going to show you what crystal lattice is. Okay. In a silicon atom, okay, you have 4 valence electrons. And if they are in one material, this is how do we see the crystal lattice of our silicon atom. Okay, so we have here a sharing or a pairing of our electrons when they are bounded together. Okay, okay. From the 4, okay, since we have many atoms in one silicon material, okay, 1, 2, its neighboring, you have here 2, 2, 2, and 2. So you have this picture, a sharing of atoms, a shared electrons rather, from its neighboring silicon atoms. Okay, so going to see how does that after. Okay, this shared electron, if you have a sharing, okay, we're going to term them as bond. Okay? You have one person and another, and they love each other. You have there the bonding. Okay, if it's just one electron or one human being, can we say I am bonding with myself? No. There should be somebody else for you to have that bond. And these horizontal and vertical lines, okay, these are what we call bonds, represented by one electron in each line. Okay? So I have shared to you earlier what is crystal lattice. Okay? So in one sheet or one piece of silicon, yes, as I've shared earlier, you have here so many silicon atoms. And you have here your bonds. Okay? Here are your bonds. And then, in this piece, sorry, this is just 1D. Okay? And this is how the crystal lattice actually looks like. Okay? I hope in your chemistry, you have done this one. Just like, can you imagine your jackstones being put up together, okay, and then we're going to form a crystal-like structure, okay. So this one here, like a 1D picture. This is how silicon looks like when it's cold. Okay, there is no potential or there is no energy being given yet. Okay, so it has no free electrons because you don't have anything. You don't have energy to push these bonds, to push these electrons from one atom to another atom. Okay, it has no free electrons. It cannot conduct electricity. Therefore, it behaves like an insulator. Because again, the definition of silicon, it will only be a semiconductor device if we give them a little amount of energy. Okay? So, how these electrons will going to move from one atom to another atom. Okay? These electrons will only move from one atom to another atom if we're going to apply heat. Okay? This heat is the energy that will allow our electrons to jump from one silicon to another silicon. Okay? An electron may gain enough energy to break free of its bond. And you have the bond. Okay? Very bare, cold, insulator. We apply a little heat. Try to observe what happened to our bond. Okay? It broke. There's a break of bond. Therefore, this one free electron now will going to move around. It will just going to wonder where it will going to be placed. Okay? Diba? The aim here is to let one silicon electron to jump from one atom to another atom. Okay? It is available now for conduction and is free to travel throughout our material. Okay? Very, very free. Okay? It has no direction. It has no direction yet because we are still allowing one electron to be freed for conduction. Okay? So if one electron leaves a bond, okay, it will going to create a hole. Okay, just like like you have a piece of paper and then you're going to take something. Of course, you're going to have a hole. There will be a gap in that. And in electronic devices, this hole is actually represented by a positively charged particle. Okay, let's give a little more character. This hole can also move and it can jump from one bond to another bond. Okay. Okay. So now, we're going to observe what happens to our bare silicon if we add more heat. Okay. 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 One heat. One electron is freed for conduction. If you have one electron that will going to break from the bond, you have there a hole. Okay. One. Okay. From the bare one, we apply heat. Okay. They broke with each other. You have here the electron and you have here the hole. Let's try to add more. Okay. Another one here. Add more and add more. Okay. This creates electron hole pairs, which will then be available for conduction for the electricity to move. Okay. Take a piece of silicon, we apply potential difference, we apply heat. Okay. When heat is released, you have there your, okay, earlier, these electrons is very, very much free to go anywhere. Okay. Because it doesn't have electric field yet because of the potential difference that will go to give the direction. Okay. But as you can see here, if we now apply the potential difference, we set up here these red lines. This is our electric field. And this is where our electrons will going to flow. I mean, well, that will be the path of our electrons to flow. Okay. I have this. Okay. Okay. So our electron now has its own path whenever it is freed from conduction. Okay. Let's try to apply more and more. Okay? Therefore, applying heat and potential, our silicon material is now free for conduction. Our semiconductor material, silicon sheet or silicon wire, can now accept electricity because there is a flow now of your electrons. More heat, more current, less resistance. Okay. Okay. I hope you understand our first part of our discussion. Okay. Later, after this one, the second video, we're going to show what happens to our silicon material if we introduce, okay, if we're going to dope them with other type of chemicals, other type of elements. Okay, later I will going to show you. Okay, that's it for our part 1 of our discussion. I hope you have learned something. Okay, goodbye guys, thank you very much.